Kia ora koutou, and welcome to Lab 5 ENEL 270. In the last few labs, we've looked at op-amps and a number of different uses. In this lab, we're going to look at some more general applications of operational amplifiers. First thing we're going to look at are using op-amps as what we call a sensing circuit using a phototransistor. A phototransistor is a device that looks like this one here. So it looks a bit like a clear LED. And what it does is it acts as a transistor with two legs, where the third pin is based upon optical incoming light. This could be infrared, visible light, ultraviolet light, or other sources. As a reminder for these labs, we're using the LMC6462 dual op-amp. We'll need to have a plus or minus 5 volt supply set up. I have this already set up here. If you're not sure how to do that, refer back to lab 2, where we talk about setting up that supply, or ask a TA. This lab starts off with some questions about this phototransistor. In this lab, we're using the PN168 phototransistor. One thing to note is that this device has two leads. These correspond to a collector and an emitter. The emitter on this is slightly longer than the collector. If you're not sure which way around this should be, you can also use the diode tester on the multimeter, which is the setting at the bottom here, which has the image of a diode, and you can use that to test your phototransistor because it acts like a diode. To do that, you can turn the dial on the multimeter to the diode transistor, making sure you have leads connected to the multimeter, and you can connect your leads across the phototransistor, connecting the positive lead to the shorter leg, which is the collector, and the negative lead to the longer leg, which is the emitter. If you do it that way around and make sure they're not shorting out, you will see that there is some voltage across this device. If you do it around the other way, so the negative leg to the collector, the positive lead to the emitter, you'll see there is no voltage across the device, which tells us this is acting as a diode. So, once you've answered these questions about this phototransistor, you're then going to build the first circuit, which is shown on page 4. This circuit is an optical sensing circuit, which I have constructed here on the breadboard. What this circuit does is uses this phototransistor to effectively measure the amount of light that we're observing in the current area. First thing we're asking you for here is a question about the configuration of the op-amp in this circuit, as well as its voltage gain. Remember that this phototransistor, while it does have a voltage across it, we put this in what we call a reverse bias configuration. You can tell that because the emitter is connected to positive 5 volts and the collector is connected to ground via a resistor. If we think of this as a diode, that would be as if we had the negative side of the diode connected to a positive voltage source and the positive side of the diode connected to ground. So this would act to block the flow of current. What the phototransistor does is then varies that amount of blocking based upon the amount of incoming light to the phototransistor. So we can think of this phototransistor as being like a current source where the voltage across it is unknown, but it will produce a certain amount of current. That amount of current depends upon how much light falls on the phototransistor. You can see here on this datasheet specification for the phototransistor that there is in fact a relationship between the amount of instant luminance and the amount of current coming out of the collector of this phototransistor. So this again indicates how this behaves. We think of this like a variable current source. Okay. Once you've thought about the configuration of the circuit and the voltage gain, what we're going to do is measure and record two voltages for the circuit, what we call the dark voltage and what we call the light voltage, if you will. And these correspond to how much light is falling upon the phototransistor. So at the moment, I have the phototransistor uncovered. You will notice in the circuit, I've put it off to the side a little bit compared to where the op-amp is. I've done that on purpose. That makes it a little bit easier to get at this phototransistor to either have it exposed to instant light or to cover it over if we want to see how it behaves in the dark. You don't necessarily have to put it that far away, but that can make things easier when you're building and testing your circuit. So what we're going to do is take our multimeter and we're going to measure the output voltage from our op-amp circuit. In this case here, I've chosen to use the bottom op-amp, op-amp A. You could use the other one as well, it does not matter. At the moment, this is uncovered. I'm going to turn the power supplies on, plus or minus 5 volts to the circuit, and I'm going to measure the voltage coming out of the op-amp. You can see in this current setting, I've got about 1.2, 1.3 volts. That amount of voltage will vary depending upon how much light there is at the time you're doing this experiment, in particular whether you're below on the ceiling lights, close to a window where there's instant light coming in, etc. So that number will change depending on your test setup. So this is answering our question about measuring the output voltage when light from the ceiling light shines on top of the sensor. To do the one before that, where we're talking about this dark output voltage, what we can do is cover over the top of the sensor and see what voltage we get. And you may need to adjust the range of the multimeter to get an accurate reading of this. The idea of this is that even though this is completely covered over and there's no light falling upon it, there's still a small amount of current flowing through this transistor. And that gives us what we call our dark current that's getting amplified to give us our dark voltage. And you can see here, this is fluctuating the range of about 50 to 70 millivolts. Again, this will vary based upon your setup and your components. Once you've taken those measurements of those voltages, you can then calculate what the appropriate current is in each of those cases and discuss whether you think, based upon those measurements, this circuit is a good circuit to use as a light meter. Do you think this is appropriate for that application? And if it is, what limitations does it have? Or if it's not, why is it not a good circuit for that? The next circuit we're going to build in this lab is another optical sensing circuit. In this case, what we're going to do is build that second circuit shown here. Note we are moving the phototransistor, so it's now connected to our negative 5 volt supply and is now going into the inverting terminal of one of our op amps. So make sure you do change that connection correctly. What we have here is a capacitor placed in feedback across our op amp, as well as a switch. Here we don't have a physical or mechanical switch. What we're going to do instead is use a piece of wire. If you can see it on the circuit I've constructed here, I have this orange loop of wire. I have both ends connected in across the capacitor, so the capacitor is short-circuited. To then open that switch, I can simply pull one leg of that piece of wire out, and they'll open the switch. At the moment, I have set up the oscilloscope following the instructions in the lab spec. Channel 1 in yellow is measuring the voltage at the emitter of the phototransistor, and we can see it's quite small and noisy. Channel 2 in green is measuring the output voltage of this circuit. At the moment, I have this switch closed. This length of wire is shorting out the capacitor, so there is no output voltage. It's shorted to ground. What you're going to do in this lab is make sure you first of all set up the oscilloscope using the voltage and time base settings in the lab specification. Importantly, make sure you set the time base to 1 second. You'll see that when you do that, the screen will take quite a while to update, and you'll only see the trace actually updating when it reaches halfway across the screen. And we're doing this on purpose. You'll see why in a moment. There are then a few questions here about this particular circuit, asking you what specifically this circuit is doing, what type of operation is it performing, and writing an expression for the output voltage of the circuit in terms of the current flowing through the phototransistor. Remember that we're treating this phototransistor in the circuit as a variable current source. And there's also a question about why we, as an engineer, would use this second circuit instead of the first one. So what is the advantage or disadvantage of this circuit compared to the first one? What we're then going to do is take, again, 2 measurements, one for when there is a decent amount of light shining on the phototransistor, and one when it is dark, which we can do both by covering it with our fingers. The way you're going to perform this measurement is, first of all, you're going to, and I'm going to show this demonstration with the phototransistor uncovered. You are first of all going to connect this short circuit across the capacitor so that you zero out all the voltage, you discharge the capacitor. You're then going to set the light level either by having it, as I do currently with just ceiling light on it, or dark and covered with your fingers. If you're going to cover over, make sure you cover over and for the entirety of this measurement. When the trace on the oscilloscope screen reaches just goes off the right hand side of the screen, what you're going to do, just doing now, is unplug one end of this piece of wire, so opening that switch, and you'll see this will start to update on the screen. When the trace reaches the right hand side of the screen, you can press the run stop button, which will pause what's on the screen here. This will then give you a ramp on your output. Again, remember I have that in green at the moment, and you can see there is a ramp on the output voltage here. You can then use the cursors on the oscilloscope to measure the rate of change or the slope of that ramp. What you'll do is you'll do that for both when the sensor is uncovered and when it is covered, and record two slopes from that. To do that, again, remember, you can restart the oscilloscope, press the run stop button to make it go green where it's actively running. You'll see in a moment the screen will update. You can then short out again across that capacitor, make sure that resets all your voltage measurements. Okay, once you're happy that's done and it's ready to go, I'm going to now measure the dark voltage. So I'm going to cover over the phototransistor, wait for this to update, and then as it reaches the right hand side of the screen, disconnect one end of that piece of wire that's shorting out the capacitor, wait for the trace to go across the screen again, and then pause the oscilloscope hitting the run stop button, and it will go red when it's paused. Again, you'll get a trace for the output that has a slope on it, and you can measure that slope using the cursors. You're going to then record both of those slopes, and therefore using those rates of change of voltages, which is what these slopes are, then calculate the current coming from the phototransistor in both cases using the expression you derived earlier for the output voltage in terms of the phototransistor current. The last circuit we're building in this lab is an analog to digital converter circuit. The important thing to note here is that we have changed our power supply configuration. So you can see that rather than having plus minus 5 volt supply to our op amps, we now have 5 volts and ground. So we'll need to adjust the power supply configuration. As you can see I've done here, I've used what was the negative 5 volt supply and changed that to be our variable V in supply. When you're building the circuit, because you have so many connections coming out from all these similarly valued resistors, you will end up with a lot of connections coming into your circuits. You'll also need to use a second LMC6462 op amp package. We need 3 op amps for the circuit. These have 2 each, so you have 1 spare unused op amp. For the purposes of this lab, it is fine to leave that spare op amp disconnected. It's up to you which op amp you choose to use and which op amp you choose to leave disconnected. Make sure you do keep track of which way around they are though, as that will matter as we're doing our converter as to which op amp corresponds to which output voltage level. The other thing I suggest doing as you're building this is to take your time, and as you can see I've done here, build your indicators, which are these 3 LEDs, out on one side of your board so it's easy to see everything in one place. If you have them scattered around the board, it can make that a little bit harder to view. You don't have to do that, but that can make your testing a little bit easier. The first thing here are some questions about the configuration of the op amps in the circuit, and then we're going to vary our input voltage between 0 and 5 volts and watch what the LEDs do as we change that voltage. So for example, you'll see here I have this left-hand power supply. I'm using that as my variable V in. I currently have that set to about 0 volts. If I power on the circuit, both supplying that 5 volts for the op amps and this V in supply, you can see currently the LEDs are off. As I dial this voltage up towards 5 volts, I'll see that these LEDs start to turn on. The way I have this set up is that first of all this red one will turn on, then the orange one I have in the middle will turn on, and finally the green one. You'll note that the orange one can be a little bit harder to see than the other two, so you'll have to look quite closely to see if it's turned on. Okay. Based upon those LEDs coming on in sequence, we can then think about how many patterns we have at our output, what options we have, and thus how many quantization levels our ADC has. Based upon the number of quantization levels, we can then determine the number of bits required to represent the outputs from our ADC, which is the resolution of the ADC. Knowing our resolution, or a number of combinations, our number of quantization levels, we can also calculate, assuming an input range of 0 to 5 volts, the voltage increment, in other words, the change in voltage, that corresponds to a change of at least one significant bit in the output. Thinking about our LEDs, that means what is the voltage change required to turn the next LED on? So we have them all off. What is the voltage change from 0 volts required to turn the first LED on, the change from that voltage to turn the second LED on, and so on. Because our circuit is nice and symmetrical, we should find it's the same voltage for each voltage change for each LED, so we have only a single change we have to calculate. Once you've calculated what that change is, we can then, using a multimeter, record the voltage at which each LED turns on. So if I enable this output here, as I turn this voltage up, we can record that here. By using a combination of this coarse dial and then some small adjustments using the fine dial, we can find out when each LED turns on. Bear in mind, depending upon which LED colors you're using and the amount of ambient light in the lab, you may have to look quite closely to see if some of them are turned on, but it should be reasonably clear. You can then record each voltage for each LED as they turn on, and thus compare what you've measured here in terms of each voltage, and particularly the change in voltage required between each stage, to what you calculated before as the voltage increment to turn the next LED on, and see if these compare to each other well or not. And if they do or don't, you can then explain your reasoning. The final thing for this circuit is to determine if we wanted to increase the number of bits of this ADC, so increase its resolution, how many extra op-amps we need to add to the circuit. So here we're asking about if we wanted to build an ADC of this configuration, what we call a flash ADC, with 8 bits of resolution, how many op-amps would we need to build such an ADC? That is the end of the main part of the lab. There is a final optional circuit using 2 op-amps to build what's called a peak detector circuit. It's reasonably straightforward. It has 2 op-amps, a diode, a capacitor, and a switch to reset that capacitor. The idea of that circuit is we can then use that to capture and hold peaks, as shown on the back page here in an example, where it's telling you how to set up the oscilloscope to do this, and also what kind of measurements you should obtain. And this kind of circuit can be quite useful as a sort of highest or lowest point detector in various different applications. It is optional for this lab, so you do not have to do that for marks though. That is the end of lab 5.